Okay, good morning. When you do your potentiometer experiment, you'll be dealing with three different potentiometers. One is what we call a linear potentiometer, or POT is the actual short name for that. So you'll often hear people talk about adjusting a POT, and they're talking about a potentiometer. It's just a shorter word for potentiometer, obviously. And the three you're dealing with are what we call linear, nonlinear, which is an audio potentiometer, and a 10-turn POT. Now, your linear and nonlinear, or audio, have about a 270-degree radius. So let me pause this video and get my pen up, and I'll show you what I'm talking about there. And when I speak of a POT like that, I'm talking about one that's got the three legs down here, typically, and it's shaped like this, and I know my drawings are not stellar, but you get the idea. So the POT can adjust from, let me use a different color there, if I can. That way it's a little more perceptible. POT can adjust from this point all the way around to about that point right there. So about 270 degrees is what we get out of those. And when you look at this chart, it explains the difference between a linear and a nonlinear. A linear POT is going to change through the scale in a linear fashion, in a straight line, just as this chart shows you. And an audio POT changes real slowly about the first half, and then changes rapidly on the second half. And both of those are 270-degree POTs. So the short-term POTs that I talked about with this very crude drawing that I gave you over here. But the reason an audio POT does that is our ears hear in a very unique fashion. And you can kind of read that in this paragraph. And I'll read that particular point. But it says, because the human ear is sensitive to sound intensity in a logarithmic, at low sound intensities, small change in intensity is perceived as a big change in loudness. So that first half of the POT, it gives us very slow change, and then that second half, boom, is a major change. And that's why when you read the resistance measurements, you get very little change through the first half, whether you're reading 10K downward or 0K upward. But then that second half, man, it ramps it up quite a bit. So that's the difference between a linear and a nonlinear, and nonlinear being an audio POT typically for volume controls in the old-fashioned way. I know a lot of our electronics today has volume controls where we just press either an up button or a down button. But the old audio potentiometers that were used were very similar to what you would find on an older car radio, usually a stock car radio, especially compared to aftermarket stuff. And a 10-turn obviously has a unique feature. It actually makes 10 revolutions around to get between the zero value and the maximum value. So if you got a 10K POT, for instance, then when the idea is when you make the first of the 10 turns, you're hitting somewhere around 1K. The second of the 10 would give you 2K. The third of the 10 would give you 3K, so forth and so on. So those are utilized where we're looking for very precise settings, something we could not get, say, with a linear POT, just because setting it to an exact value would be very difficult. But with a 10K, or 10-turn, a 10-turn POT, setting to that exact value would be much easier, because we've got 10 full 360-degree turns that divides that POT, as opposed to this crude drawing I show you that had one less than 360-degree turn to get from zero to the full value. So obviously a 10K would give us some precision that we wouldn't have with their other counterparts. So hopefully that gives you some additional information on potentiometers or POTs. And as always, if you have any questions, please let us know.